Welcome back to Calculus 1. We're looking at limits and the derivative. This is section 2, example number 8, parts A, B, and C. So for part A, we want to find the limit as x approaches infinity, or as x becomes extremely large in the positive direction, of the function f of x is equal to 1 over x. Notation, we write it as this: the limit as x approaches infinity, and now we put our function in here, 1 over x. Let's just go ahead and make that look a little bit better. So what I'm going to do is I'm going to draw out a graph so you can get a visual representation of this function. And using this visual, we should be able to tell what the function is doing as x becomes larger and larger. So we'll go from 1 through 4 here, but of course we would want to go out towards 100 million or so. And I'll make a little table, but you're going to be able to see very quickly what's going on. So when I plug in 1, I get 1 out. When I plug in 2, I get a half out, which is redundant in what I just wrote there, but that's 0.5. When I plug in 3, I get a third out, which is 0.3 repeating. And when I plug in 4, I get a quarter out, which is 0.25. And of course, we want to keep going in each of these. The question is, what does f of x go towards as we approach infinity for our x value? But just remember that x can't actually be equal to infinity because infinity is not a number. We just use it as a representation for an idea. So here we've got a height of 1 out. When I plug in 2, I get a height of a half out. Okay, so on and so forth. Now, if you look at this function, you can tell that it's getting closer and closer to the x-axis. But the idea is that it's never actually going to hit the x-axis. So, for this particular problem, it looks like the limit value is going to be 0. So let's go ahead and say that this guy is equal to 0. Now the function is never equal to 0, mind you. But as x becomes larger and larger, the function values get closer and closer to 0. Okay, now let's take a look at the next one. This is b. So we want to find the limit of 2x plus 1 over 3x plus 1. The trick that gets used a lot is to divide every term in this particular rational function by the highest x power. Okay, so what I mean by that is the highest, for each of the terms they all have like an x or a variable in them. Whichever one has the highest power, you're going to divide by that many x's. Okay, so let me go ahead and show you here what I'm talking about. So these next two problems will demonstrate this idea. Now you might ask, well, isn't there a problem by dividing by x? What if x is 0? Then we certainly can't divide by x. But here's the key point. As x goes towards infinity, or as our variable goes towards infinity, it's not equal to 0. It's equal to some other value. So there's not a problem there. The function that we're going to use for the replacement behaves exactly like the original function. The only difference is the new function doesn't have a hole at 0 where the old function does, or where it's not even defined. Okay, so the new function is going to be, I'm going to divide everything by x because x is the highest power I see in the numerator and the denominator. So when I do that, this is going to reduce. So here's our replacement function. I get 2 plus 1 over x divided by 3 plus 1 over x. Now those two functions are the same. The original function and that function are the same. The only difference is 0 is not in the domain of the second one, but not an issue because we're not going to be working with values near 0. So we rewrite this as the limits of, now we can split this guy up if we want to using our limit laws that we've covered already in this section. And we already know that second limit is 0. And that's because we just did that in the last problem. Or the last example, I should say. So what do we get? Well, the limit of a constant is that constant. The other guys are 0. And so when we do this reduction, we get 2/3 for the value. Now let's go ahead and take a look at problem C. Again, we're going to divide by the highest power of x, which is going to be x squared. And so that's going to be our replacement function. And those two functions behave exactly the same way except for at 0. So the first function is defined as 0. This new function that I'm going to write down right here is not going to be defined at 0. Again, it's not a problem. So we're just going to divide everything by x squared because that's the highest x power in the top, the numerator, and the bottom, the denominator. Let's just make this a little bit larger here. Now notice we're approaching negative infinity, so we have to be a little bit careful there. It's not going to pose a problem here, because whether we approach negative infinity or positive infinity, those back values that are divided by the x, those guys go to 0. So as x becomes really, really large, either positive or negative, in this case the negative, 3 over x goes to 0, 2 over x squared goes to 0, and also 1 over x squared goes to 0. You should check those on your calculator, graph them out, and make sure that, yes, they do actually go towards 0. So what do we get? Well, those back pieces all go to 0. And so this guy up here is going to be equal to the following. So those other pieces are going to go to 0, and so this is just equal to 5.